So in the first four parts of our discussion on gases, we focused our attention on the definition of pressure, which we know, of course, is a measure of the force a gas exerts against its container walls to the area that force is being exerted against. And of course, we broke this down into a proportionality, where the pressure is proportional to the two things that affect the force of the gas, those being how many particles there are and how fast they're moving, which is a function of temperature. And that area really is a function of the volume of the container the gas is in. If there's a bigger volume, there's more surface area for the particles to collide with. And we derived all of our simple proportional gas laws from this understanding. But in a problem like this is not a changing condition problem, because I do give you three conditions of a gas, but none of them change. And yet I want to know what volume we have. Now, it would be lovely if this proportionality were in fact an equation, because then I could plug in the moles of gas that I'm given, I could plug in the temperature, and I could plug in the pressure and simply solve for the volume, if this were an equation. But it's not, and here's why. The units of pressure are atmospheres, and the units of moles are moles, and the units of temperature are kelvins, and the units of volume are liters, and an atmosphere doesn't equal a mole Kelvin per liter, so this is not an equation. However, it can be made an equation. Like most scientific relationships, you can turn the relationships or proportionalities into an equation, often by the addition of a constant. And the constant we need to add to this to make it an equation is something called the ideal gas law constant, R. And if we want to find out what R is, we could do that, knowing a few simple facts. For instance, all gases have the same molar volume at STP. And that molar volume is 22.4, pen's having difficulties today, 22.4 liters per mole of gas. That is true of any gas at 273 kelvins of temperature, standard temperature, and at 1 atmosphere of pressure, standard pressure. So I could turn this proportionality into an equation if I knew a certain pressure that was always associated with a certain number of moles at a certain temperature and certain volume. I could find out what this constant is right here, this ideal gas law constant. And based on the facts that we know about molar volumes, we could fill in all four of these quantities and find what the constant is. Because if we talk about molar volume at standard pressure, the pressure is 1 atmosphere. If we talk about molar volume, we're talking about 1 mole of the gas. And if we're talking about molar volume at standard temperature, we're talking about a temperature of 273 kelvins. And of course, if we're talking about molar volume, we're talking about a volume of 22.4 liters. So with everything filled in, I could isolate R by a little bit of algebra and find out what its value is. The algebra is quite easy. First, I'd want to clear the denominator, multiply both sides of the equation by 22.4 liters. 0.4 liters. And the volume would cancel from this side, but not this side. And then, of course, I would want to divide both sides by 1 mole and by 273 kelvins. 1 mole and 273 kelvins. And whereas the moles and kelvins will cancel from this side of the expression, they enter this side of the expression. So whatever this value is, it would equal the gas law constant. So very simply, the constant would equal 22.4 divided by 273 essentially, which rounds off to 3 digits of 0.0821. But most important is that you recognize the units of the constant. They are liter atmospheres per mole Kelvin. I know that sounds like a lot to say, but it's critical that you remember these. Liter atmospheres per mole Kelvin. Now, the very definition of the word constant is that this is true at any conditions. This numerical value remains constant for any gas under any conditions. And therefore, in any gas problem whatsoever, you can use this constant. So let's go back to our original problem here and see how easy it is to solve now. Let me do some erasing, and let me rethink this original problem that we had. First of all, we are given moles, we're given a temperature, and we're given a pressure of 2.5 atmospheres. And we're asked for a volume. And the second I read that this is a gas, I immediately write down something that's true of any gas, anytime, anywhere. And that is that there are 0.0821 liter atmospheres of it for each mole Kelvin of it. And I can use this anytime I want. So now, we've been learning to solve problems by starting with the answer. We're asked for a volume, and there's a volume in the ideal gas law constant. So I'm going to start with the answer. 0.0821 liter atmospheres per mole Kelvin is the answer to my problem. There's my answer. However, there are three quantities that I don't want. I don't want a pressure, I don't want an amount, and I don't want a temperature. So they must be canceled. Well, the only thing that cancels a temperature is a temperature. And so, of course, it has to be in kelvins, because only kelvins would cancel kelvins. The only thing that cancels moles would be moles. And I'm given 3 moles of gas. So moles would cancel moles. And the only thing that cancels a pressure would be a pressure. And I'm given 2.50 atmospheres of pressure. The atmospheres cancel, and I'm left with my volume. And it comes out to 28.9 liters. As a second example of a use of the ideal gas law, I read this problem here, which gives me a mass of oxygen and a volume and a temperature of the gas. Now, right away, because it's a gas, I'm going to write down the one thing in life that's constant, that there are 0.0821 liter atmospheres of gas per every mole Kelvin of gas. And since it's oxygen, O2, I've really another piece of information. Namely, I've been given a molar mass because oxygen is 32 grams per mole. So there are some hidden gems of data in amongst these actually given pieces of data. And one of the gems, of course, is when I'm talking about a gas, I am given the gas constant. And when I've identified the gas, I've been given a molar mass as well. So now we'll do the problem like we do all problems. We'll start with the answer. And the question that's asked here is, what is the pressure? Well, I look at all of my data. I see a mass, I see a volume, I see a temperature, I see a mass, and I see a number of moles. The only place that I see my answer, namely a pressure, is right here in the ideal gas law constant. So I start with the answer. 0.0821 liter atmospheres per mole Kelvin of oxygen. There's my answer. Of course, there are numerous quantities here that I need to cancel, one of which is volume. And the only way you can cancel a volume is with a volume. Fortunately, I was given 20 liters of the gas. I need to cancel the temperature of the gas. Well, I was given a temperature, and that temperature in kelvins would be 298 kelvins. And temperature cancels temperature. Finally, I have to cancel moles. And the only other place I see moles is in the molar mass of the gas that I've been given. So to cancel moles, I will invert the molar mass. 1 mole of oxygen is 32 grams of oxygen. And moles will cancel moles. Of course, I still don't have my pressure because I have to cancel mass. The only thing that cancels a mass is a mass. And that's why I was given 10 grams of O2. And when I take out my calculator, I get 0.382 atmospheres of gas. Lovely application of the ideal gas law. One last example, just to drive home the point of how we should approach these things. Sorry this is a little messy, but through magic, all those bits of lines have vanished. And I read the problem. I'm given a mass of carbon dioxide, and I'm given a volume, and I'm given a pressure. Most importantly, I know something about carbon dioxide. Its molar mass. Carbon dioxide represents 44 grams per each mole. And because this is a gas, I can always cling to the ideal gas law constant for answers. Liter atmospheres per mole Kelvin. Now in this problem, I'm asked for a temperature, and I like to start with the answer. Mass is not a temperature, volume is not a temperature, pressure is not a temperature, mass and moles aren't temperatures. The only place I know the temperature of a gas is right here in the ideal gas law. However, I would have to invert this ratio so that I get a temperature and not an inverse temperature. So I rewrite the ideal gas law constant by saying there's a mole Kelvin of gas for every 0.0821 liter atmospheres of gas. In other words, I've simply inverted the ratio. And now I have my answer, a temperature of gas, right there. Of course, there are certain quantities I wish to cancel. One of them is volume, and the volume will cancel the volume. I also want to cancel pressure, and I have a pressure to cancel that pressure, but first I have to convert millimeters of mercury to atmospheres, because millimeters of mercury won't cancel atmospheres. Or I can convert atmospheres to millimeters of mercury. 1 atmosphere equals 760 millimeters of mercury. And atmospheres cancel and are replaced with millimeters of mercury, but I can use the millimeters of mercury of the gas to cancel those. And we're almost home. We have our temperature, but we still need to cancel moles. And the only place I see moles is right here in the molar mass of carbon dioxide. There are 44 grams CO2 for every 1 mole CO2. And moles will cancel, but I still have to cancel mass, and fortunately I was given a mass. So I divide by 50 grams, and the mass of CO2 cancels the mass of CO2, and I'm left with the temperature of this gas. And I get a value of 320 kelvins. But of course, the last step in problem solving all year has always been to check units. We wanted Celsius and not kelvins, so I'm going to have to subtract 273, leaving me with a Celsius temperature of 47 with correct significant figures, 47 degrees Celsius. One final example that I'll race through is once again, well, we'll save this for another day because this is a stoichiometry problem. So hopefully these examples have shown how just knowing the ideal gas law constant itself, I can find a volume, a pressure, an amount of gas, or a temperature anytime I want, as long as I'm dealing with a gas. That's the key. And yes, some people learn the ideal gas law and plug numbers in, plug in their pressures, their volumes, their temperatures, their moles, and their constant. But by doing it this way, by using just the constant and starting with the answer, you won't accidentally try to plug in a pressure that isn't liters, or a pressure that isn't atmospheres, millimeters of mercury, or a volume that isn't liters, or a temperature that isn't kelvins, because the gas law units wouldn't allow any of those other units besides the ones needed. So therefore, I recommend this method.